Hello, my name is Ievgen Iosifov, and today I'm going to present our work, Prototyping Methodology of End-to-End Speech Analytics Software. We will start from our previous publications. We have highlight few of them: technique comparison for natural language processing, sentence segmentation from unformatted text, analysis for automatic speech recognition, pipeline for training, automated speech recognition, safety of speech information, and speech emotion recognition transferability. All these previous works work as preceding to this building of prototype that organizations can use in production in order to deliver value to the customer. As of prototype, there's few frameworks in the market that works for speech recognition. There's few approaches how to build it, but there is not comprehensive approach and recommendation and experiments on how to build end-to-end business software based on models of speech recognition, emotion recognition, NLP frameworks, etc. Now it's independent modules, and our main goal of this paper is to describe and make a prototype for end-to-end solution that can be put into organizations production mode and can be used to deliver value to end customer, I mean business, organizations, etc. Our related works that we see is, let's start with NEMO. NEMO is, let me choose laser, NEMO. This is a toolkit for building AI applications. And this toolkit does not provide any storage, any database. It's interface toolkit, basically, where you can upload or choose an audio, and result will be either transcription or emotion. It is very flexible toolkit. It can do a lot of speech recognition and NLP tasks, but it is not end-to-end in terms of business value. It is only NLP and speech tasks. That is not enough, from our opinion, for business customers. Another one is ESPNet. ESPNet is end-to-end speech processing toolkit, where you can upload or train your own model, fine-tune speech recognition model, add some specific task based on the speech, like speech emotion recognition, dearization, etc. And then you can use this toolkit once again to make very small, narrow tasks of speech recognition, for example. And the third one, as we can see, is Kaldi Speech Recognition Toolkit. Once again, it's only for minor blocks or tasks like speech recognition, diarization, emotion recognition, embedding, etc. So all of these three frameworks limited only to speech-related tasks or NLP tasks, and they do not have any storage, they do not have any queuing logic, any clustering, etc., etc. So it's only building block where what organization can use to build this software. So we have defined few inputs, few requirements for our prototyping. It should be loose coupling. It should be pipeline flexible in pipeline term, and interoperability. Let's start from the pipeline flexibility, because loose coupling we will be defined later, next slide. So pipeline flexibility means that we do not know exactly which task will the business customer need at the very end of implementation. Hence, we need to make it as module architecture as possible. You need to add one more task, not a problem. You do not need to change all other components. It should be like microservices. So it should be flexible, it should be easy, it should not change anything of already existed in your prototype or your software solution. Interoperability. That's not a separate environment, and software works in real time, like software environment. Organizations have CRMs, BI system, a lot of data lakes system, a lot of systems that these software should be integrated into. That's not an independent software. It works with contact center solution, with CRM solution, with telephony solution, etc. So it should be interoperable. And let's go to the loosely coupled components. So these components should be very interchangeable. If you need to change some data formats and protocol between components should be independent of data structures and underlying frameworks. You as a user of this prototype, you should not think about what data structure or what framework I can use in this or that part. You can use any. And the main thing you can change in any moment of time, any component or framework without changing your data structure. Also, as another definition is asynchronous processing for non-interactive tasks. In real-time live scenarios, we have real-time tasks and non-real-time tasks. For example, we need analyze something, organization needs analyze something in order to improve quality of customer to organization, communication, etc. This is non-interactive task, and we can queue and we can postpone this task. So we need to deliver this. And we should be able to deploy and update components independently. As the first task to build a prototype was protocol selection. And we were compared real-time and non-real-time protocols. For real-time, for sure, it's like there's complexity for prototyping. Real-time is harder to prototype than non-real-time because you do not need to make all the work to deliver this in real time in client and server architecture. You can just store the information. Applicable cases range for business life. It's more as of today non-real time, basically analytics, suggestions, coaching, based on this recognition of and linking of organization needs to customer feeling, etc. So much more for non-real-time scenario, at least of today. And computational requirements for real-time, it's higher. For non-real-time, you can do these postpone queue, so you need less requirements. That's why for prototype we choose to go only with non-real-time. We have some parts for real-time as well, but that was not a focus of our prototyping. As a framework, we have compared two, from our opinion, most useful for these kind of prototypes, Nemo and from NVIDIA and Kaldi. And here is a list of what Nemo can do very good. So it's very easy, and I mean, comparatively to other frameworks, it's easy to fine-tune model. in this is very important for business cases, for organizations, in order to add lexicon, acoustic characteristics, etc. You need to fine-tune your speech recognition models for this particular business case. And here's like Nemo, one of the easiest and best in the class. No need that's for this fine-tuning as well. You do not need to have grapheme to phoneme models in order to fine-tune, to change vocabulary, not vocabulary, I'm sorry, to change lexicon, to change graph, etc. And this is ready to go server-side framework to serve models. From the other side, there's very famous Kaldi framework, and the main advantage of Kaldi is, for example, acoustic model is not biased for language model task. As of NEMO framework, there is two-part acoustic and language model, and acoustic, unfortunately, acoustic model during training and fine-tuning gets some characteristic of language model and remembering and learning and how words should work with works. And so it biased for language model task, and you can't improve this with adding language model because acoustic model is already biased. And fewer audio needed, so dataset is smaller dataset needed to train Kaldi models for the same accuracy. For prototype, we decided to try both of them and implement for both of them. Once again, loose coupling, you remember from the previous slide, and that was our main goal, that you can use any framework without even thinking how data structure should work. So as of implementation, there is a few parts that should be done in prototype. There's only NLP and speech-related tasks here, but you can see that even this small amount of, like, you need just to process audio and store audio, still need at least 4 tasks. Speech recognition, mono audio dearization to stereo. Still in business cases, there's a lot of mono recording, normalization to normalize words into number to convert, and punctuation. That's a minimum number of tasks that need to be fulfilled for business case. And for version 1, we started with version 1, and then we will go to version 2. We started with very simple architecture and algorithm. We input audio stream within API post method, HTTP post method. We return result ID immediately. So we queue this and then started to recognize audio stream, post-processing task like punctuation, like diarization, normalization, and storing result into the DB, and that's it. And the customer can, after this finished, can request get by ID, result ID, get all text results. How it works on component level, we have API and backend side. For prototype, we in paper have more detailed framework selection for backend and API. This is a fast API framework, very flexible and very easy to be built API on. We have ASR level, we have post-processing level, and we have database. So when you input audio file, backend gives you, through API, gives you result ID that you can use in future to request your data. And then after this, close the connection and start in processing of your audio. First is speech recognition level, then normalization, punctuation, diarization, and then store all the results to the backend. So quite simple logic. Version 1 We will go to limitations of this version. There's a lot of limitations of this version 1, and that's why we implemented version 2. I will start with algorithm, and then we'll go to the component level. First of all, in version 2, we decide either these by the flag that we can receive through API from the customer, either this real time or non-real time. And if it is real time, we recognize and return result immediately at the same to the same channel. Usually for prototype, we decided to go with WebSocket simplest for real time. And if it is not real time, it's simple asynchronous API, HTTP REST API. So we once again return to the customer result ID, but instead of immediately recognizing audio file as in version 1, we create QA task for recognition and post-processing. The main limitation of version 1, I will return to version 1, was without queuing algorithm, we receive a file and we immediately start to recognize. And if something inside of recognition process as of now, it will degrade performance significantly. So in version 2, we added this layer of queuing. And if recognizer is not ready, I mean, like, doesn't work, that's one scenario, or overloaded, that's another scenario, then it wait. And when recognizer is ready, the recognizer took this QA task and start recognizing audio file, and after that running post-processing, and after that storing to database. And on component level, it is still relatively simple, a little bit more comprehensive, but simple still. We have real-time connection, WebSocket through HTTP, and we have asynchronous non-real-time for REST API. And when you send a file, first of all, backend put it into the queue. And then when the recognizer's ready, they took from the queue and recognize and put back like, I'm done. And then post-processing level, once again, when they're ready, each of them, they took from the queue and then return to the queue, I'm done, and result. And we also add indexing. We'll go a little bit, and in the end we store everything to database. It is much more reliable, much more like ready for production. We also add instant search indexing layer in order to deliver results through backend API even faster, and basically as it's written for instant search for the content. We presented code example snippet of fast API code example, how to deliver these endpoints on API level for both WebSocket and HTTP. I will not go deep here, but in paper you can be familiar with this. And that's how it looks like after you put this code example into fast API. It generates you very easy, very understandable swagger about what should be in required, and in parameters you can choose. So let's once again return to difficulties with this implementation. So first of all, even with version 2, prioritization of real time. We do not know, and we for sure when real time file will be streamed. I mean, will be received. And if during the receiving of real-time request, we already have overloaded recognizers, then this prioritization should be improved in order to deliver real-time with the highest priority. Stability. We need to store with version 1. It was very unstable. With version 2 is much more stable, but still there's a place to improve stability. Cluster mode to implement few recognizers if something is not going well on the recognizer. It's stuck, it's paused, it's down, etc., etc. So in stability level, there is still a space for improvement. Scalability. Once again, for cluster to add easily more recognizers, post-processors, we need to increase number of channels from 100 to 300. That shouldn't be a problem in real-time case, and you just add a few servers, load recognizers there, and they automatically should connect. And feedback and visibility. One of the limitation of both first and second version of current prototype, that's a prototype, so we know this, is feedback and visibility that business users will need. So you need to know how many tasks in the queue, you need to know which stage you have each of your file or stream, so you need to have this visibility and feedback. That's the end of my presentation, and I would like to thank to Ender Turing OU for defining these business problems and inspirations, and for sure computational resources to build these prototypes on. As a result, we tested the prototypes and it delivered stability if the number of processed audio is less than real time, like 1 hour per one vCPU, and managing a load balancing of connections and audios to process is a task to be solved in the following version of prototypes, or not prototypes, business solutions, as well as prioritization of real-time processing against non-real-time. I mentioned already in the limitation. And we will also focus on optimization issues such as scaling, parallelization, security, visibility, etc. Thank you for your attention.